Quasi-hereditary algebras, lecture 16, generalizations, stratified algebras. Let us start with our setup. Let K be an algebraically closed field and A a finite-dimensional K algebra. We fix some order on the set of representatives of the isomorphism classes of simple A modules. So our simple A modules are L1, L2, and so on, all the way up to Lk. For this fixed order, we can define the standard module delta I, where I is between 1 and k, as the quotient of pi modulo the trace in pi of all the projectives pi plus 1, pi plus 2, and so on, all the way up to pk. And we can also define, for any I between 1 and k, the costandard module nabla I as the intersection of the kernels of all homomorphisms from the injective envelope I sub I to all the injectives I sub I plus 1 and so on, ik. So all these were defined for quasi-hereditary algebras, so we take this general definition. And then we have the category F delta of all A modules which admit a standard filtration, and the category F nabla of all modules which admit a costandard filtration. So these are the filtrations whose subquotients are standard or costandard modules, respectively. Now we go to define a new class of modules, which is called the proper standard modules. Definition. For any I between 1 and k, we define the proper standard module delta overlined I as the maximum quotient of delta I with the property that the simple module Li appears in the proper standard module delta overlined I exactly once. So in other words, the module delta overlined I is the quotient of delta I by the trace of the projective module Pi in the radical of delta I. So the module delta I has Li on top, and this should be the only simple subquotient of delta overlined I which is isomorphic to Li, which survives. Note that the trace of Pi in the radical of delta I coincides with the trace of delta I in the radical of delta I. And directly from the definition, we have that the multiplicity of Li in delta overlined I is 1. And this implies that the endomorphism algebra of delta overlined I coincides with our original field K. While in general, the endomorphism algebra of delta I is just a local algebra of dimension the multiplicity of Li in delta I. For example, if the algebra A originally was local, then this means that k is equal to 1, and the standard module delta 1 is by definition projective, so it's the indecomposable projective P1, while the proper standard module delta overlined 1 is the simple top of P1, so that's a simple module L1. And now we have defined the proper standard modules, delta overlines, and we have the corresponding category F of delta overlined, which is the category of modules with proper standard filtration. That is, with a filtration with proper standard subquotients. Dually, we can define proper costandard modules. Definition: for any I between 1 and k, we define the corresponding proper costandard module nabla overlined I as the maximum submodule of the costandard module nabla overlined, which has the property that the multiplicity of Li in nabla overlined I is equal to 1. In other words, the module nabla overlined I is the intersection of the kernels of all non-injective homomorphisms from nabla I to I. Or, equivalently, nabla overlined I is the intersection of the kernels of all non-injective homomorphisms from nabla I to nabla I. In particular, directly from the definitions, the multiplicity of Li in nabla overlined I is 1, which implies that the endomorphism algebra of nabla overlined I is trivial. It's isomorphic to the field. And again, in general, the endomorphism algebra of the costandard module nabla I is a local algebra of dimension the multiplicity of Li in nabla I. And an example, if A is local, then this means that k is equal to 1, then the costandard module nabla 1 is just the indecomposable injective I1, while the proper costandard module nabla overlined 1 is the simple socle of I1, so it's a simple module L1. And again, we have the category F nabla overlined of all modules which have a proper costandard filtration. That is a filtration with proper costandard subquotients. So now we can define our main protagonists for this lecture, the standardly stratified and properly stratified algebras. Definition: our pair consisting of our algebra A and our fixed order on the set of representatives of the isomorphism classes of simple A modules. So this algebra is called strongly standardly stratified, or SSS algebra, provided that the left regular A module belongs to F delta. So this means that all projective A modules have a standard filtration. And our algebra A is called properly stratified, provided that the left regular A module belongs to the intersection of F delta and F delta overlined. In other words, all projective A modules have both a standard filtration and a proper standard filtration. Remark the general stratified algebra, so standardly stratified algebras, that's a more general notion which is defined with respect to a partial order on the set of representatives of the isomorphism classes of simple modules. So in this lecture we will discuss only linear orders, and this gives us this strongly standardly stratified algebras or properly stratified algebras respectively. So the general stratified algebras were defined in the paper by Klein, Parshall and Scott with the name stratifying endomorphism algebras, which appeared in 1996. And properly stratified algebras were defined by Dlap in his paper Properly Stratified Algebras from 2000. Here are some examples. Example 1. Every local algebra is properly stratified. As we saw, in the local case, the unique indecomposable projective is a standard module, and the simple modules are proper standard modules, so this means that the indecomposable projective has both a standard and a proper standard filtration. Example 2, every quasi-hereditary algebra is properly stratified because one of the definitions of the quasi-hereditary algebra says that for quasi-hereditary algebras, standard and proper standard modules coincide, and projectives have a standard filtration. So any quasi-hereditary algebra is properly stratified. So here is a third example. Consider the algebra A given by the following quiver. We have two vertices 1 and 2, an arrow alpha from 1 to 2, and an arrow beta from 2 to 1. And the relation beta alpha beta is equal to 0. So this algebra is an SSS algebra, but it is not properly stratified. So let's look in detail in its projective, standard, and proper standard modules. So for the projectives, the projective P1, we start at 1, we follow alpha to go to 2, then we can do beta to go back to 1, then we do alpha to go to 2 again, and then we are stuck because of the relations that beta alpha beta is 0. So for P2, we start at 2, we use beta to go to 1, we use alpha to come back to 2, and then we hit the relation. So these are our indecomposable projectives. And of course, by the definition, since 2 is greater than 1, the standard module delta 2 is the projective module P2. And if we take P1 and kill all the occurrences of 2, what remains is just the simple module L1. So delta 1 is L1. So in particular, L1 appears once in delta 1, so the corresponding delta over line 1 is also 1. But 2 appears twice in delta 2, and if we kill the second occurrence of 2, we see that the module delta over line 2 is just 2 on top and then 1 underneath this 2. So these are our projective, standard and proper standard modules. And now we see readily that projective modules have standard filtration. P2 is delta 2, and P1 has P2 as a submodule, and if we factor out it, we get delta 1. At the same time, the projective modules do not have a proper standard filtration. The proper standard module delta 2 overlined is 2 on top of 1, but delta 2 or P2 has 2 on top of 1, which is on top of 2, and that's it. There is a 1 missing here, so P2 does not have a proper standard filtration. So this algebra is an SSS algebra, but it is not properly stratified. Okay, so the main result for today is the following theorem, which compares the category F delta with the category F nabla overlined for an SSS algebra. So theorem: if A is an SSS algebra, then F delta is homologically left orthogonal to F nabla overlined, and F nabla overlined is homologically right orthogonal to F delta. This means that F delta coincides with the category of all A modules M, such that xi from M to n is 0 for any n in F nabla overlined and for all I greater than 0. And also, F nabla overlined coincides with the category of all modules n, such that xi from M to n is 0 for all m in F delta and for all I greater than 0. So the major part of today's lecture will be devoted to the proof of this theorem. And our proof goes by induction on K, on the number of simple modules. If K is 1, then A is a local algebra, the standard modules are projectives, and proper costandard modules are simples. So F nabla overlined is just A mod, modules which are filtered by simples, and F delta is just A projective modules. So in this case, the claim of the theorem is clear. In order to prove the induction step, let us first discuss the inductive nature of the definition of stratified algebras. Let us denote by curly I sub k the ideal of A, which is given by the trace of the projective module pk in A. Then the quotient algebra A modulo ik has the same simples as A, apart from the simple lk, which is killed because we kill the trace of pk in A. In particular, our linear order on A simples restricts to a linear order on simples over A modulo I sub k. It is an easy observation that the algebra A modulo I sub k is an SSS algebra with respect to this restricted order. This follows directly from the definitions. Also, it is clear that any module over this quotient algebra is also an A module, so we have a natural embedding of the category of A modulo ik modules into the category of all A modules. And we have a theorem which is similar to the quasi-hereditary case, that this embedding of A modulo ik modules into A modules is homologically full. In other words, for any A modulo I sub k modules x and y, and any degree I greater than or equal to 0, the degree I extensions from x to y as A modulo ik modules are isomorphic to the degree I extensions from x to y as A modules. And the proof of this is very similar to the corresponding statement for quasi-hereditary algebras. Now let us proceed with the proofs of our main theorem. We start with proving that the category of modules with costandard filtration is right homologically orthogonal to the category of modules with standard filtration. And for this, we need just to show that all extensions of positive degree from all standard to all proper costandard modules vanish. And because we just discussed the inductive nature of the definition of stratified algebras, it is enough to consider extensions from the standard module delta k to costandard modules, or from standard modules to the proper costandard module nabla overlined sub k. The module delta k is projective, so for it everything is clear. So let us consider the degree I extension from delta j to nabla overlined k, and let us prove that this vanishes by induction on j. If j is equal to k, we just said that that's true. So in order to prove the induction step, we consider the short exact sequence where pj surjects onto delta j with some kernel ker. The module ker is filtered by standard modules delta s, where s is strictly greater than j. So by induction, we may assume that all x from the kernel to nabla overlined k vanish. And now, by dimension shift, we get that all extensions of degree at least 2 from delta j to nabla overlined k vanish. So it remains to show that the first extensions vanish. And in order to do this, let us consider a minimal injective co-resolution of nabla overlined k. So nabla overlined k is a submodule of ik, which is nabla k, and the cokernel is embeddable into a direct sum of copies of ik by the definition of nabla overlined, because it's a maximal submodule of nabla overlined k, which has only one copy of lk. And so, now if we apply to this minimal injective co-resolution, where y1 is a sum of copies of ik, if we apply the functor hom from delta j, where j is smaller than k, then due to the fact that delta j has no lk as a subquotient, we have that hom from delta j to y1 is 0. And this means exactly that the first x from delta j to nabla overlined k vanishes. So we are done with the inclusion of f nabla overlined to the right homological orthogonal to f delta. And in order to prove the converse inclusion, we prove a much stronger statement. We actually prove that the category of all A modules, for which all first extensions from standard modules vanishes, already this category belongs to f nabla overlined. And here the proof is also quite similar to the quasi-hereditary case, so let's go through the details. Consider a module n for which all first extensions from all standard modules to this n vanish, so it belongs to our right-hand side, and let x be a maximal submodule of n which doesn't have any subquotients of the form lk. So we have the corresponding short exact sequence that x is a submodule of n and the quotient is n over x. If j is smaller than k, then, of course, there are no homs from delta j to n over x, because by our definition, the socle of n over x consists only of lk's, and delta j doesn't have any lk. And so, by dimension shift, the first x from delta j to x equals the hom from delta j to n over x, and this is equal to 0. That's because the first x from delta j to n vanishes. And now, by induction on k, we get that x belongs to f nabla overlined, and hence all extensions from all standard modules to x vanishes. So in particular, from the long exact sequence, it follows that the first extension from the standard modules to n over x vanish. And it remains to prove that n over x has a proper costandard filtration. Note that the first extension from delta k to n over x vanishes because delta k is projective. So in order to prove that n over x has a proper costandard filtration, we proceed by induction on the multiplicity of Lk in n over x. If this multiplicity is 0, then n over x is a zero module, so this belongs to F nabla overlined. If the multiplicity is 1, and n over x is not nabla k overlined, then, due to the definition of nabla k overlined, there is a simple module Lj where j is smaller than k, such that the first x from Lj to n over x is non-zero. But this first x embeds into the first x from delta j to n over x, and we get a contradiction. So if our multiplicity is 1, then our module is nabla overlined sub k. So now, to prove the induction step, let y be some submodule of n over x, which is maximal with respect to the properties that the multiplicity of Lk and y is 1. Then we have the corresponding short exact sequence, y embeds into n over x, and we have a cokernel. So if j is smaller than k, then the functor of Homin from delta j vanishes on all terms of the sequence, because all sockles contain only copies of L sub k, and delta j doesn't have L sub k. In particular, since the first extension from delta j to n over x vanishes, it follows that the first extension from delta j to y also vanishes. And from our proof above, we have that y is actually nabla overlined k. And in particular, we have that all extensions from all standard modules to y vanish. And so from the local dimension shift in degree 1, it follows that the first extension from the standard modules to n over x over y vanish. And since the multiplicity of Lk in our cokernel is strictly smaller than the multiplicity of Lk in n over x, our claim that n over x belongs to F nabla overlined follows by induction. And this shows that F nabla overlined contains all A modules for which the first text from all standard modules vanish, and this of course contains all A modules for which all x from all standard modules vanish, and this completes the proof of our main theorem, or the first part of the theorem. And the fact that F delta is left homologically orthogonal to F nabla overlined is similar and is left as an exercise. Here are some consequences of this. Corollary: the following conditions are equivalent. Condition 1, A is an SSS algebra. Condition 2, all projective A modules have a standard filtration. Condition 3, all injective A modules have a proper costandard filtration. Condition 4, for the algebra A op, the left regular module has a proper standard filtration. Proof. So the first two conditions are equivalent by definition, and the last two conditions are equivalent because they are connected by the k-duality. And the fact that the first condition is equivalent to the third condition is exactly the claim of the previous theorem. And in particular, we see from here that the notion of a stratified algebra is not necessarily left-right symmetric. So the correct statement is that if A is an SSS algebra, then A op is an algebra for which projectives have a proper standard filtration. But for properly stratified algebras, for those which have both standard and proper standard filtration, we get an easy corollary that an algebra is properly stratified if and only if the opposite algebra is properly stratified with respect to the same order. Now we can discuss tilting modules. Let A be an SSS algebra. Definition: an object in the intersection of F delta and F nabla overlined is called a tilting A module. Theorem, which is due to Agoston, Happel, Lukács, and Unger. Claim 1. For each I between 1 and k, there is a unique up to isomorphism in decomposable tilting A module Ti, such that delta I is a submodule in Ti, and the cokernel of this embedding has a standard filtration. Claim 2. Each indecomposable tilting A module is isomorphic to Ti for some I. Claim 3. The Ringel dual of A is an SSS algebra. So here the Ringel dual is the opposite of the endomorphism algebra of the direct sum of all indecomposable tilting modules Ti. And this is an SSS algebra with respect to the opposite 2-hour order. And the second Ringel dual is Morita equivalent to A. And this is proved very similarly to the quasi-hereditary case. And just like in the quasi-hereditary case, our characteristic tilting module T is a generalized tilting module. But now the interesting difference with the quasi-hereditary case, in the quasi-hereditary case, A always had finite global dimension. For stratified algebras, the algebra A may have infinite global dimension. And this theorem is proved in the paper by Agoston, Happel, Lukács and Unger, which is called Standardly Stratified Algebras and Tilting. So now another interesting different feature of stratified algebras compared to quasi-hereditary algebras is that we have now a separate theory of cotilting modules. So assume that A is properly stratified. Then a cotilting A module is an object in F delta overlined intersecting with F nabla. And we have the following theorem, due to the same authors, that for each I between 1 and k, there is a unique up to isomorphism indecomposable cotilting A module Ci, such that Ci surjects onto nabla I, and the kernel has a cos-standard filtration. Then each indecomposable cotilting module is isomorphic to Ci for some I, and we have the corresponding Ringel dual, which is the endomorphism algebra of the direct sum of all cotilting modules, and then opposite. That's an SSS algebra with respect to the opposite order, and taking this thing twice gives you an algebra which is Morita equivalent to A. And this follows from the previous theorem using the K duality. Please note that the module C is in general a generalized cotilting module, and still A can have an infinite global dimension, and also that this R' of A might fail to be properly stratified. So that's a difference with a quasi-hereditary case. We have a separate theory for tilting modules and for cotilting modules. Let us consider one example in detail. Let A be the path algebra of the following quiver with relations. We have two vertices 1 and 2, an arrow alpha from 1 to 2, an arrow beta from 2 to 1, and the loop gamma at 2. And the relations are gamma square is equal to beta gamma is equal to alpha beta is equal to 0. So here are the projective and injective modules. So P1 we start at 1, we follow by alpha to 2, and then we go by gamma to 2, or we can go from 2 by beta to 1, and then we hit the relations. And P2 starts at 2, we can do gamma to stay at 2, or we can do beta to go to 1, and then we hit the relations. I1, it starts at the bottom at 1, we can come to 1 by beta from 2, and to this 2 by alpha from 1. That's I1. And I2 starts at the bottom from 2, and we can go to this 2 by alpha from 1, or by gamma from 2, and to this domain of gamma we can write by alpha from 1. So these are the projectives and the injectives. And now we can see that the standard modules and the proper cos-standard modules are as follows. So delta 2 is just P2, and if we kill P2 inside P1, we see that delta 1 is just the simple module L1. So proper cos-standard modules, so we see that nabla overlined 2 is 2 in the socle and 1 on top of it, and if we kill it here on top, it remains 1 in the socle, so nabla overlined 1 is just 1. And we readily see the standard filtrations of projective modules, and the proper standard filtrations of injective modules for our algebra. So our algebra is an SSS algebra, but it is not properly stratified because projective modules do not have proper standard filtrations and injective modules do not have costandard filtrations. I2 is a costandard module and there is no quotient of I1, which is I2. Great, so here are the tilting modules. Of course, the indecomposable tilting module T1 is 1 because it's both standard and proper costandard. But the module T2 is a new module. We take the projective P1 and we can see that we can put one additional L1 on top of it. Here on this 2 we can put a 1 and connect them via alpha. And we get this module, which as we can see has a standard filtration, so that's a delta 2 inside, and the quotient has 2 1s. And this module now has a proper costandard filtration. We have 2 1 here, 2 1 here, and 1 here as a submodule. So these are our tilting modules. And to describe the endomorphism algebra, the linear dual of our A, we denote by zeta the unique non-trivial endomorphism of T2, so it sends this copy, this to 1 to this to 1, kills this 1 and kills this to 1. We denote by Xi the embedding of T1 into T2 here. And we denote by eta the projection of this one onto T1. So this top 1 constituent of T2 is projected onto T1. And it is easy to check that the endomorphism algebra of T1 plus T2 is generated by eta, zeta, and Xi. And it is also easy to check that these generators satisfy the relations zeta squared is equal to 0, eta after Xi is equal to 0, and zeta after Xi is equal to 0. And now if we take the opposite algebra, we see that the linear dual of A is actually isomorphic to A. And note that our algebra A is not properly stratified, so it doesn't really make sense to discuss cotilting A modules. Finally, let us note that properly stratified algebras appear naturally in several different contexts. For example, they appear in generalizations of category O for Lie algebras, which is discussed in my paper Stratified Algebras Arising in Lie Theory. Stratified algebras also appear in the usual category O, but now for Lie superalgebras, which can be found in the paper by Anders Frisk, Typical blocks of the category O for the queer Lie superalgebra. Okay, some problems and questions at the end. Problem question 1. Prove with all details that delta overlined I is the quotient of delta I by the trace of delta I in the radical of delta I. Problem question 2. Prove with all details that A modulo Carly I sub k is an SSS algebra. And prove with all details that the embedding of the module category over this quotient into A mod is homologically full. Problem question 4. Spell out all the details in the proof that n over x has a proper costandard filtration. And problem question 5. Prove with all details the theorem by Agustin, Happel, Lukács, and Unger about tilting and cotilting A modules. Thank you very much and see you next time.